I'm here to talk to you guys today about how to combine a hybrid approach and a hybrid approach, which is a combination of engineered and machine learned features to enable agents to play Minecraft using human demonstration data. And so looks like there's a bit of a delay. Okay, what is MineRL and what is Minecraft? Minecraft is a sandbox game that lets you play with placing blocks in a voxel grid format. And MineRL is an API built on top of Minecraft that allows you to control agents using RL or just machine learning in general. In this case, they have a bunch of predefined tasks, and you're able to sample the agent to do random actions, or you can do it more intelligently using machine learning. And the guys who invented MineRL built this competition called the Basalt Competition. And what they did is they collected 40 to 80 different executions of humans playing the game for tasks in increasing difficulty. So the first one is finding a cave, followed by making a waterfall, followed by creating an animal pen and trapping an animal in it, followed by building a house. And all of these tasks are representative of different things that you might do in Minecraft, but are very difficult to define as a reward function. I mean, what exactly is finding a cave? What exactly is building a house? There's a lot of room here to sort of express yourself through an agent. Our approach to this problem was using machine learning, which we wanted to have lifelike tasks, so we wanted to take the data and use behavioral cloning. In addition, we wanted to use a rule-based approach. In many cases, the task that can be solved in front of you requires a fixed set of commands that humans can do really well, and we can extract those and use them. And we can combine the two to provide, using human feedback, to sort of improve how these agents perform over time. And so this solution actually ended up winning first place in this competition, and so I will explain to you how we got there. And so our approach overall is a state machine system that uses a state classifier. The current state of the machine, the game is given by an RGB image. It's 64 by 64, which is fairly low resolution, but we may do with it as well as having these human demonstrations. That's all we were provided, is access to the simulator and the human demonstration data. And so the first thing we did is we built this state machine. We classified each of the different states of solving a task. Finding a cave is searching for the cave. I found the cave, go towards the cave. I'm in the cave, throw the snowball, I'm done with the trial. We built up these state machines as the complexity of the task increased. The state classifier, we annotated by hand not each, but a lot of the demonstration data that they provided in the competition. We were allowed to provide up to 30 megabytes of our own data to supplement the human data. Obviously, you could imagine we could use a GAN and explode our demonstration data, but we were really restricted. They were really trying to see how we could exploit the data given by the human demonstrators, as well as not use too much compute time. We were limited to 12 hours of compute time to train and execute all of the tasks on our agent. We also built this estimated odometry system, which allowed the agent to figure out where it is based on the sequence of actions that it got there. And then we have all of these different modules underneath that sort of keyed the behavior of what the agent is doing. And I'll walk through how each of these were implemented, one of them being a behavioral cloning system. And we'll start with the state classifier. So the state classifier has 13 different labels. Has cave, inside cave, I'm not sure what I'm looking at. All of these were kind of enough to encompass each of the tasks. And so we had one big state classifier for all of the different tasks that we had in front of us, and we used our own custom GUI to label all of them. Overall, we had 81,000 different samples labeled using a simple convolutional model followed by a fully connected network. I'm pretty sure most of us are familiar with this exact design for doing image classification. And it was extremely accurate at solving this problem in general. And so then I'll talk about the state machine system that we built. It's a finite state machine, exactly what we were taught in CS theory. Our state classifier triggers the transition between states when we need to enter a new state or when we should stop being in the state and maybe go back to a previous one. So this is the map that we use to handle the make waterfall task. And so we start at we're in the world, we're in a random state, and then we want to see, does it have a mountain? Because we want to place the waterfall at the top of the mountain. If it has a mountain, go towards it. Otherwise, search around until you find one. And what we're looking to do is just really discretize these things in a very intelligent way to both leverage the behavioral cloning, which was really good at exploration, and leverage what we're also very good at, which is building an automaton to handle a fixed set of tasks. And in this end case here, once I'm at the top, that's when we execute a fixed strategy. And I'll show some videos of this agent doing that. We'll talk about now the behavioral cloning process that we implemented. It's just using imitation learning directly off of the training data. We process the human demonstrations, masked certain actions. We don't really want to run or sprint. Maybe pressing 1 or 2, which gives a different item in the agent's hand, is not really useful for the particular task. So in most cases, we threw those out, reduced the state space. This greatly simplified the problem and didn't require any additional data to prune what we had access to. In fact, leaving the space bar in was probably one of the smarter things we did, because that really makes it look a lot more human-like when it's playing the game. And now we'll talk about how we combined this engineered approach and the deep learned approach. Each of these engineered subtasks implemented by a human designer. So for example, finding a cave at the end of an episode, it's very straightforward, throwing the snowball. In the case of placing a waterfall, we want to run up to a position, place a bunch of blocks, drop the water bucket, run back, turn around, look at it, take the snapshot. And if we're building a village house, maybe we find a nice wide open space, we want to go to that wide open space. All of these things can be planned in a fixed way. And now I'll talk about the estimated odometry. What exactly were we trying to do here? Well, it's really important for some tasks to know where we were. And we were not allowed access to the internal state of the simulator because they wanted to make it as real-world-esque as possible. So we used a simple point model to model the agent. If it moved forward, we increased the position in space. Obviously, if it runs into a wall, we're not really handling that case, and that's something that we could do in the future to improve it. But most players were running into walls too for some reason, so it didn't look too weird. There were a lot of cases where the player just wouldn't even do the task. I'm not exactly sure what they were thinking. So this is the odometry estimation interface. We're showing the actions taken at each time step as a tensor. We have the estimated pose of the agent over time. We have the agent's position in red. Agent's trajectory, this white line here. We have the outputs of the state classifier as confidence intervals over 0, 1, and the classified states at each position. And if we step through a particular demonstration, we can see that the agent updates its position as well as lets us know things like, is this an open space? And this is very useful for really understanding exactly what's going on inside of the state classifier. And some sample trajectories of the agent. We have a find cave example, make waterfall, just showing the human-like behavior that you can kind of observe by combining this behavioral cloning and feature-engineered solution to this particular problem. I will note that in the build animal pen, we often had a problem where the agent couldn't really tell that there was an animal. Honestly, I couldn't either. It was this like 1 pixel chicken that was white, and it was impossible to tell. So animals were a big problem with 64 by 64. Some additional results, we evaluated all of these agents by hand using the true skill metric. We had 4 baselines that we wanted to test. The whole system as it was, the engineered solution alone, so if we just used a by hand algorithmic approach, using behavioral cloning by itself, and also the human demonstrations. So we just presented all of these things to a bunch of human judgers, very similar to how the competition was actually evaluated. And we asked the question, which of these two is better? And we calculate all of the results for comparing 268 of these different pairs over 7 different people. And the results were kind of what you expected. The human example was the #1 overall, followed by the hybrid approach, which was the second, and the engineered approach was third. And behavioral cloning was, as expected, pretty bad. It just really doesn't capture the behavior. But I thought what was most interesting, and I think this is actually why we ended up winning the competition, is our make waterfall agent was actually really good, and it tricked the judgers into thinking that was the better agent or the human player. And so the hybrid approach worked best in the best performer and more human-like case. For fastest performer, the algorithmic approach ended up winning out, as you might expect, because it's very quick and sort of just beelines it to certain places. And you can see all of these results and more in our paper publication. So the key takeaways here is, this did end up winning first place. There were other approaches. They ended up maybe leaning more heavily on the reinforcement learning and deep learning approaches and generating data. We showed that this hybrid intelligence solution is actually able to learn and perform well at playing Minecraft for these poorly defined tasks. And that we really can leverage our domain knowledge to push these deep learned agents further. All of our code base is publicly available, and feel free to take a look at our publication on arXiv if you want to learn more. And we had a lot of references in our paper. And any questions, feel free to contact me. Thank you so much.